Okay, so in this video, I'll be going to illustrate to you the depth first search. This will be another searching algorithm in your algorithms and complexity. So let's start with for depth first search. In this one, this is a graph traversal and search algorithm that explores as much as possible along each branch before backtracking. So it somewhat starts as the root node and explores each branch thoroughly before moving to the next branch. So it can be implemented using the recursion or a stack. It's somewhat useful for something like finding connected components, cycle detection, and topological sorting. So in this case here, we are finding the shortest, the path in that given nodes. For example, we wanted to search a specific nodes in our tree where it could be a graph. So we are going through into the depth the depth of your tree or the graph first before we will do or we will deal with the backtracking algorithm. So when we say backtrack, you have to go back into the um path that you've been visited earlier. So you have to go back in order for you to find another way, to check in other ways as well that was not visited yet. Next will be the depth first search steps. So for the steps here, then you have to start at the root node. You have to begin the search from the root node or any arbitrary node in a graph. So mark the node as visited to avoid revisiting it. So in our graph or in our tree algorithm or data structures, we are searching that specific nodes in our graph or a tree. So we mark that as visited. Then once you were able to meet the dead the dead end. So you have to check further in other ways. You have to go back. You have to move back in your previous path, and then you will check another node if there will be unvisited nodes then. Now, you have to visit the current node. This means processing the node, like printing its value, adding it to a list or etc. So for visiting the current node, you were actually processing or visiting that particular node. You were able to insert that in your stack. And afterwards, if you're able to be in that and already, there's a time that you will have to make sure to do whatever pop those element in your stack and then you have to insert another once you were able to find another entry or nodes in your graph. Next, you have to explore and visited neighbors. So you have to look out or look at all adjacent nodes or neighbors at the current node. Select one neighbor, usually the first and visited one, and recursively perform the DFS or the depth first search from that neighbor. So if there will be, for example, you do have a graph or a tree, then once you were able to have or meet the dead end already, so you have to backtrack, and then if there will be another ex- successor in the previous path, so you have to um make sure that you were able to visit those elements as well. The neighbor will be another child, if there will be child notes or another child notes that we were not able to visit yet. So make sure that you have to exhaust everything before doing the backtracking in the previous path if there will be another child notes to be that you have can visit with. Next, you have to recurse deeply. And this one, you have to move to the neighboring node and repeat the process. Visit the node and explore its neighbors. That means to say you have to continue this process to depth first, meaning you will visit all the neighbors of the current node before backtracking to explore other path. As what I mentioned, you make but you have to work on it. You have to check at the deepest level in order for you to backtrack, or you must be in the dead end already before you will perform the backtracking. So the backtrack, once you reach a node with no unvisited neighbors, you have to backtrack to the previous node where unvisited neighbors are left. Continue this process until all the nodes in the graph have been visited or until the algorithm explores all possible paths. So in this case, actually, you have to make sure that you were able to expose first in that particular hierarchy before you will go back sure. If you are already in the dead end in that particular way or graph, so you must actually go back into the previous path and check if there will be another um element that you can check with. Then you have to terminate the search. For terminating the search terminates when all nodes have been visited and no unvisited nodes remain to explore. In this case, since we are having or we're just searching a particular element, so if you were able to find that element, for example, you found that element in the fourth level, and if that's the case, that you are able to find that element already, so you have to return the value. You have to make sure that you are able to identify what level is that located and everything. So what will be the representations later? It will be breakthrough in the example as well. So the time complexity for this one, we have the O notation of V plus E, where the V, that is the number of vertices or nodes in our graph, and your E, that is the number of edges in the graph then. So that is not driven, and that time complexity denoted in that time complexity. Since the time complexity of depth first search is determined by the number of nodes, which are your vertices, and some edges that the algorithm needs to traverse. So in this case here, in BFS, each vertex is visited exactly once. So for vertices, the time complexity contributed by visiting the node is O of V particularly. Now, for each of the vertex, DFS explore its neighbor via the edges, its edges. So every edge in the graph, that means to say that you were able to expose, you were able to check. So every edge in the graph is checked once. Therefore, the time complexity from traversing edges is O notation of E. So that's why the overall time complexity is the sum of the time which we take to explore all vertices and the edges as well. So since the time complexity of the vertex is O of V and the time complexity of edges is O of E, so given the time that you're searching, so it must be adding the vertex as well as the edges. That's why it is O of V plus E. I hope that is clear for everybody. Now, for the space complexity, we have here the recursive call stack as well as the iterative call. Now, pertains to the space complexity, that is O notation of vertex. The space complexity depends on how they graph is stored and whether the DFS is implemented recursively or iteratively. So in this case, the recursive version of the depth first search is the function calls to itself recursively. That means to say that there is a base case and each call is added to the system call stack. the maximum depth of the recursion will be the number of vertices in the worst case. So like in the case of a long path in the graph or a deep tree. So in this case right now, that is O of vertex in the iterative as well. We explicitly use a stack to keep track of the node to visit. The maximum size of the stack is O notation of B as well as in the worst case, all the nodes could be on the stack at once, like in a graph or tree with a deep and branch path. So therefore, the total space complexity for recursive as well as in iterative is the O of B. Because in recursive, due to the call stack and the visited array, and for the iterative, mainly due to the stack used to keep track of the nodes. So I hope so that that is somewhat clear for everybody. So in the next video, I will be going to illustrate, on how we could be able to illustrate this in a graph already, how we could perform this searching algorithm. So see you in the next video.